So when you think about outer space, at least when I think about outer space, when people say outer space to me, I think about things in outer space. So just, let's get warmed up here. What's that? There we go. Sun. Comet. Saturn. Does anybody know which moon this is? It's my favorite moon. This is Enceladus. Enceladus has this great habit of kind of shooting out a stream of ice that forms one of the outer rings of Saturn, which is just really amazing to me. It's one of my favorite things. So these are all things in space, okay? This isn't outer space itself. These are things in space. What I'm interested in is not the things in space, but the space. And as you can see, it looks a little boring from here, and you have to look really carefully to make it interesting. But I promise you, it's a very interesting thing. Okay. So if you go to your local neighborhood astronomer, or if you go to a conference or you go to the literature and you ask about outer space, they'll kind of look at you funny. What I'm talking about when I talk about outer space, some people call the interstellar medium. Okay? This is the stuff that's out there that isn't in things. It isn't in planets, it isn't in stars, it isn't in black holes, it isn't in spaceships, it isn't in aliens. It's in sort of diffuse material. It's stuff that if you were in it would feel like a vacuum and would suck out your eyeballs. Okay, that's what we're talking about when we talk about the interstellar medium. But I don't like the term interstellar medium. You notice I didn't title this talk The Interstellar Medium. And I'll tell you why. So let's just take this apart. So medium here means stuff. So the interstellar medium, if I meant, small, medium, large, interstellar medium would be an extra large, and I'll talk about that more later. But here I don't mean medium in terms of that. I mean, it's the material. Okay, fine. Also don't mean it holds seances. Inter is, of course, between, and stellar means stars. So this is the stuff between the stars. The reason I don't like this is the same reason that I don't call the ocean the interfish milieu, or the sky the interbird material, right? If you talk to the birds or you talk to the fish, they tell you that the material that they are living in isn't just the stuff between them. It has all sorts of properties that are very important. It has some relationship with the material in it. And it's not that it's between the stars. That's not what makes it interesting, okay? It has an interesting relationship with stars that I'll talk about a lot today. But it's not just the stuff between the stars. That, and when I'm talking about outer space, I'm not just talking about the interstellar medium, I'm talking about the interplanetary medium, so that's the stuff amongst the planets. The interstellar medium, going up in larger scales here, the intra-cluster medium, the material around clusters of galaxies that you actually just heard about in terms of the intercluster light, and then the intergalactic medium, the material on the larger scales, okay? So all of this I'm going to consider outer space, and I'll sort of take you on a tour of this stuff itself, the outer space itself, and I'll try to tell you why I think it's important, and some cool things about it. And yeah, so that's the general gist. Okay, so this is a line with dots on it. The purpose of this line with dots on it is to tell you something about scale, okay? Scale is crucially important when we're talking about the outer space and its diffuse material. Each one of these dots is going to represent, the space between these dots is going to represent a factor of 1,000, okay? So this is 1,000 between these two, it's 1,000 between these two, so between these two we've got 1,000 times 1,000, which is a, there we go. And 1,000 times 1,000 times 1,000 is there we go, okay, good. So these are the scales that I'm going to be using throughout this talk. And whenever I show you an image, I'm going to show you on its scale. I'm going to show you somewhere along this factor of 1 billion scale. So my smallest scale, the smallest thing I'm really going to consider, more or less, is the entire solar system. Okay, so this is like the orbit of Pluto, side to side, roughly speaking. About 200 astronomical units, or a thousandth of a parsec. So that means that my next step up is a parsec. That's this guy here, and that's the sort of typical star-to-star distance. Now, you don't need to know that this is what a parsec is. A parsec is 3.26 light years, or 3 by 10 to the 18 centimeters, or whatever. It's just some scale, okay? So you can just think about this as like our typical scale here of the distance between stars. If you go into like a cluster of stars, it'll be closer. If you go out into deep space, it'll be further. But right around here, our nearest star, about a parsec. Okay, fine. If you go by another factor of 1,000, you're talking about the sort of smallest scales upon which we talk about galaxies. A dwarf galaxy might be a kiloparsec, 1,000 parsecs. And if you go up one more scale, by a factor of 1,000, you get to the galaxy cluster. So these galaxy clusters that we just got an introduction to, Abel 21, whatever, is about a megaparsec in scale. Okay, so solar system scale, a milliparsec, a parsec, a kiloparsec, and a megaparsec. Now, I say parsec a lot, and this is all sort of confusing. Let's put this on a more human scale. Let's take the whole thing and shrink it down. Okay? So I'm going to make another one, but for human size. So you can kind of get a sense of what I'm talking about. And this is a scale that you're sort of personally familiar with, I hope. So on the small scale, we're going to go with the thickness of a dime. So this translation is going to be from parsecs to meters. So I guess it's a factor of 3 by 10 to the 16, if you care. But anyway, so the thickness of a dime is going to be my smallest scale. And I used to have a picture here of just a toddler. When I first gave this talk, it was 3 years ago, and I just gave a picture of a toddler, but now I know what this scale is. This is the size of my son, who is about 1 meter tall. Okay, so max peak is there. Now if we go another factor of 1,000 above max peak, if you could get my son and make 1,000 copies of him, God help you, and lie him all down in a row, you get something about like the scale of the Hopkins campus. Okay, so thickness of a dime, max, Hopkins campus, and then I don't know if there is a megameter, but if there were, it would be measuring California. California is about a megameter, about 1,000 kilometers. Okay, cool. So when I show this, when I show an image, if you want to think about it on the human scale, you can. Just sort of shrink the whole thing down in your head. It might be easier to relate to. So when you're thinking about that factor of a billion, when you're thinking of that factor of a billion, oh dear, I have to skip through all my slides again. When you're thinking about that factor of a billion, you can either think about this scale, or you can think about this scale, either way. Okay. So why am I telling you about all these scales? Yeah, you're talking about outer space, it's lots of space, probably want to get a sense of scale, but it's very, very important in the context of the outer space. And now why is it important in the context of outer space? Well, outer space, as I said, it's like a vacuum. There's almost nothing there. It sucks out your eyeballs, you die, it's just nothing, it feels like nothing, but there's a little bit of something, okay? And the thing is, when you have a big volume of space, even if it has a very low density, it adds up to a huge amount of mass, okay? So if you look at this guy, right, if you were to take a volume that were this big and go up by a factor of 1,000, well, you're going about a factor of 1,000 this way, a factor of 1,000 this way, and a factor of 1,000 this way. So now we're talking about a factor of 1 billion. So when you look at something on this scale, the volume from here to here is a factor of 1 billion. 1 billion, 1 billion, 1 billion, okay? So this is a quintillion or something, I forget. But if you multiply all these things together, you're talking about a gigantic, enormous volume of space. And so even though the density is very low, the total mass of it becomes very high. Okay, so this is why I'm trying to explain this. I want to just make one other somewhat weird point. So this is the scale of the entire universe, from the human scale all the way to the entire observable universe that we know of. So that's about Earth. That's about as big as you could ever spatially experience walking around, taking an airplane. This is going all the way up to the scale of the entire universe. So I've expanded my scale ever so slightly just for this slide. This is all of time. This is a human lifetime, about 100 years, say, and then this is the age of the universe. So the universe is much bigger than it is old. In terms of your perspective from a human, yeah, you know, it's really, really old, but it's really, 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 really and a half big. Okay? So that's just something to keep in mind. The universe, while it is very old, it is really much bigger than it is old. Okay. I'll leave that weird point with you. You can mull on what that might possibly mean. Okay. So let me try to give you some reasoning why I think this outer space is so important. So this is the mass energy budget of the entire universe. This is all the matter and energy that exists in the universe. Einstein told us that matter and energy are this interchangeable thing. That's the stuff that inhabits all of space. And 73% of it is composed of this dark energy, the Nobel Prize for which was given in 2011, shared among a number of people, including a resident here. Dark matter makes up the next biggest chunk. And that's 23% or so of the universe. It's probably some kind of weakly interacting massive particle. We don't know that much about it. People are looking. But the next biggest chunk is this outer space. Okay? There is about 8 times as much of this outer space that I'm talking about than there is of stars and black holes and planets and spaceships and aliens and us. Most of it is actually in this diffuse material because there's so much volume. Even though the density is extraordinarily low, space is so big, and it's so big on 3 sides, that you end up with much more material in this plasma and gas than has actually been collected into stars. Okay, so that's one reason you might be interested in outer space. There's a lot of it if you put it on a scale. But here's another budget that's pretty important. the NASA 2014 astrophysics budget, okay? And I'm using this as a stand-in. We don't need to talk about the dollars and cents, but I'm using this as a stand-in in terms of what astronomers are interested in, okay? And what astronomers are most interested in, it turns out, is cosmic origins, okay? And if you think of the origin of everything in the universe, of you, of me, of the Earth, of the sun, of every galaxy, basically, if you had to say it standing on one foot, which I will now attempt to do, diffuse material collapses under gravity. You start with diffuse stuff, and by gravity, it collapses into things. The origin of everything came from this diffuse stuff. So if we are indeed interested in this cosmic origin, where everything came from, we have to get back to this diffuse outer space, all this stuff suffused throughout our universe, which is intimately connected, I hope I will make clear over the course of this talk, with the material that's there, with all of the stuff that's in the universe and the diffuse material throughout it. Okay, so these are two maybe pretty good reasons to be interested in the interstellar medium, the intergalactic medium, the outer space itself. But here's my favorite reason. I argue that there are three types of beauty in the entire universe, okay? The first type of beauty is beauty inside the solar system. So here is a picture of Saturn taken by the Cassini mission. This is Mimas and Tethys, I think. This is the shadow of the rings being cast on the surface of Saturn. I mean, it's just exquisitely gorgeous. So this picture and all of the history of human art and every picture you've seen inside the solar system, I'm going to put in one category of art. Very beautiful, beautiful, beautiful thing. Okay, great. The next category of beautiful things in the universe are piles of stars. And this is a lovely picture of a pile of stars, roughly speaking, a cluster of stars. But once you've seen one, you kind of seen them all. There's really, a bunch of stars together. It looks pretty, but that's all you got. And absolutely everything else beautiful in the universe is outer space. So this is an image I made recently. It is a big slice of the hydrogen in our galaxy. It's about 40 degrees tall, and it goes all the way around the sky. And I'll just let you look at it moving. This is the galactic plane. This is moving higher up into the galaxy. These are some artifacts I've been trying to correct this morning. And you can see all of this beautiful, beautiful, rich structure. So every time you see images like this, all these nebular images, what you're looking at is the outer space. So scientists all claim that why they study what they study is to answer some deep question. I will not tell you that. I'll tell you I study this stuff because it is beautiful and because I'm really engaged by it. And so this is the kind of beauty I get to deal with every day, and that's what I'm trying to bring to you today. So there'll be lots of pretty pictures, hopefully, during this talk, and I hope they'll both be pretty pictures and some kind of deeper understanding. Okay, great. So here's my outline. First, I'm going to talk about material flowing out of objects into outer space, so forming outer space from stars and planets. Then I'll talk about dirty outer space. Outer space is surprisingly dirty. Then I'll talk about forming things out of outer space, and then I'll talk about outer space on the grandest scales. So this is going to be the sort of structure of the talk. So forming outer space. So I'm not going to give too many diagrams in this talk, but this is the central diagram of the interstellar medium. So I'm going to come back to this a few times, so it's worth looking at. This is the interstellar medium here. This is the outer space. And stars, both low-mass stars and high-mass stars, form out of the outer space. And then as those stars die, they return the material to outer space. So this is this cosmic recycling. This is one way in which all of the stars in our galaxy and in other galaxies are intimately connected with this diffuse material. And we know that there's this important relationship, and it really governs how stars work. It governs the formation of planets. It governs the formation of galaxies. So this recycling is absolutely crucial and critical. So right now we're going to be focusing on returning material from stars, low-mass stars, returning them into this diffuse material. So I'm going to start really close to home. You can see we're off the bottom of the scale here in terms of size. It should probably be down here, down there. And what you're seeing is material blowing off the sun. I wanted to show you this nice movie to make it clear that the sun, even the sun itself, is actually interacting with outer space. You think about it as this ball just sitting there in the middle of nothing, but really it's blowing off material. And it's losing material about 10 to the minus 14 solar masses per year, so not very much. It's not like it's going to run out anytime soon, but it's really nice to see that this is going on, and these kinds of coronal mass ejections that you're seeing, these bursts of material that blow off, can actually have effects on our satellites, can have effects on our power grid. So this outer space is actually a much more personal thing than you might have thought otherwise, and I think it's a really pretty movie. Going to a larger scale, this is a planetary nebula. I did this talk for the first time long before I knew that I was coming here, so it's actually very nice to show lots of Hubble images here in Hubble's home, so that's very cool. This is a star like the Sun that's slowly dying and sloughing off material. You can see it's about a light year across. It's much bigger than the scale we were talking about before. And this is the slow process of dying. And this process is really important because it enriches this outer space we're talking about with metals, with various material that's being built in the star. So there's this process of nuclear fusion. It builds up higher and higher element number elements that then suffuse out into the outer space. And so you're seeing this process, this relationship going on. And this particular process is very important, again, for this ecosystem, for this recycling and this chemistry. This is one of my favorites. You've probably seen this before. This is Mira. Mira is a star that was known to the ancients. Mira means miraculous. And it was called miraculous by the ancients because you could see it during some parts of the year, and then during other parts of the year, it would just disappear. And nobody really knew why it would do that. And actually, as part of my work as an undergraduate, I worked on some models, and we sort of came up with this theory that what's going on is that as the star sort of pulsates, it gets hotter and colder. And as it gets colder, the atoms in its atmosphere will form into molecules. And those molecules actually take the form of sunscreen. So your sunscreen may actually have titanium oxide in it. And that same titanium oxide, among other titanium composites, is being formed in the atmosphere of this star. But as it's doing this, as it's pulsating, it's also blowing off material. And as it streaks across the sky, and this is over the course of many thousands of years, it's actually sloughing off this material. This is an image from the Galactica satellite that's showing the material sloughed off of this star in the ultraviolet from reflected light. So you're both getting to see this really beautiful, magnificent star and the effect that it's having on its interstellar medium, on the material around it, as it's returning material slowly back to the outer space. Okay, so we just talked about the sort of slow sloughing off of material of stars about the same mass of the Sun. But if you go to more high-mass stars, they die in a much more cataclysmic way, and they go through a supernova. And they'll form a black hole or a neutron star at their core, where they were, and send off an enormous shockwave. And this makes for really gorgeous images. You've probably seen this image of the Crab Nebula. This was a supernova that went off in 1054 Common Era, and you're seeing nitrogen and hydrogen and oxygen here from Hubble, and then the glow in the center is actually X-rays from the Chandra Space Telescope. And you've got this extraordinarily beautiful image showing you how this material how this shockwave is reacting on its surroundings. And this reaction is actually crucially important. It's not just the material being returned from these stars that's critical, but it's actually the energy that they're imparting. And this is something I'm going to come back to, this process of feedback, the idea that if you set off this explosion inside of this material, that's going to have an effect on the galaxy as a whole. Okay. So we're going on a larger scale here. This is actually an image, not as beautiful, but I think really compelling, by my advisor, Carl Hylas at Berkeley. Does anybody recognize this constellation? Yeah. Yeah, exactly. So this is Orion. This is the Orion Eridanus bubble, as coined by Carl. This is the galactic plane here. So if you're sitting inside the galaxy, so we're looking at our galaxy, if you're sitting inside it, it sort of looks like a line, right? Because it's a plate. So when you look at that plate, it looks, you get this line. But these, right here in Orion's sword, is a thing called the Orion Nebular Cluster. And it's the closest cluster to Earth where massive stars are being formed. So these are the kinds of stars that go off in supernovae. And there are these gorgeous images of the stars that are still there. But some of those stars have already exploded. In fact, if you look at the ONC, what you see is this sort of like explosion-looking thing, like a bomb went off. And indeed, many stars, many of these high-mass stars have already exploded. And what they've done, excuse me, I knew I was going to do that. Back? There we go. And what they've done is made this huge bubble. This gas is, this plasma here in blue is being shown, and the X-ray is being shown in blue, and it's this bubble of hot gas that's bursting off of the galaxy. And it turns out it's very important that these stars are dying together. One thing that had befuddled astronomers for a long time is that if you just put the energy from stars randomly inside of a diffuse material, it won't have the effects that we see. But it turns out the fact that stars are born together means they also die together. And so they'll send their shockwaves out basically at the same time, allowing you to build these super bubbles. The green here is the neutral gas, and then the red is cooler ionized gas in H-alpha. Okay, so we can't see this happening. That's why we run computer simulations. This is a slice of a galaxy, a simulated galaxy, with stars blowing up inside of it. So you can see these cavities being blown open by sequences of stars exploding. The blue stuff and the green stuff are denser gas. That's the stuff that you saw in green in the previous image. And you're seeing really this extraordinary effect where huge cavities can be carved out by repeated explosions from massive stars. And we know this is very important for regulating how, not only how stars die, but also how stars form as these shock waves explode in the current forming of stars. We'll get back to that point. And it's actually very important for us because this is the sun here. And this is a little diagram from a paper I like. This is the galactic plane, and this is about the scale of all of the outer space in the galaxy. These dense black blobs are denser parts of the interstellar medium, and this huge cavity around us is called the local cavity. It turns out within about 100 parsecs of the sun, so that's the scale here, remember that's a parsec, so about 100 parsecs. About 100 parsecs of the sun, there's this sort of empty spot. There's still material there, but not as much. And it's been carved out by a series of explosions from hot stars. And we're still trying to figure out exactly how much hot material is living near the sun and maybe cooling down a little bit. It may still be pretty hot. Still trying to figure that out. But you can see that there's these little blobs of stuff surrounding the sun in this local cavity. Okay, so I gave you a little bit of sense of the material that has flowed out from stars when they die. But let's talk about this material itself a little bit more. So astronomers, as you may know, are sometimes really good at naming things, right? We name things like, I don't know, magnetar. It's kind of a cool name, right? It sounds cool. Or like how physicists call them quarks. I really like that name. But sometimes we take missteps. We call things like type 2p something something, or one of those long phone book names. Planetary nebula, famously bad because it has nothing to do with planets. Just sort of looks like a planet when you look at it with a bad telescope. And we made the same mistake with dirty outer space because we named these little sooty particles dust. And, oh, right, so here's our little sooty particles that are in the outer space. And you can see there's all this dark stuff here, right? But it isn't dust, right? This is dust. This is what you would call dust at home. Does anybody know what household dust is made of? It's made of skin and hair and other terribly gross things. Now, outer space is also gross, but it's not gross in this way. Outer space's dust is much more made of stuff that's akin to car exhaust, soot, sand, kind of carbonaceous material. It's a range of different small particles, and it goes from sort of large molecules up to sort of tiny rocks. But it has this effect of making outer space really sooty and full of material. Indeed, if you took outer space and you condensed it down to the density of air, you couldn't really make out your hand in front of your face. That's how sooty it is. It's extremely full of this sort of junky material. And you can see it yourself if you just go out on a dark night. So here we're looking at a very small scale again. And if you go out on a dark night just after sunset, what you'll start to see is this glow that's pointing towards where the sun just set. And you have to get it the timing just right. What we're seeing here is the zodiacal light. It's light that's in the zodiac. And the reason you're seeing it is that there is dusty material that's left over from the formation of our solar system. So as our solar system formed, material formed into a disk, and that stuff formed into planets. And you end up with these rocky bodies. The rocky bodies bounce against each other, and they form this dusty stuff. And you can actually see it just with your own eyes looking out into our solar system. Now, you can also see it on a bit larger scale through a telescope looking at the Pleiades. Here what you're seeing is these fine filamentary features of dusty material. And the dust here is reflecting the light. These are sometimes called reflection nebulae from the stars. So here you're seeing this outer space being lit up by the stars, and we think that the fibrosity here is actually being governed by magnetic fields. So I'm not going to talk too much about magnetic fields today, but they're also a really important constituent of outer space, and indeed they make up a lot of the energy that's out there in outer space. But my favorite way to look at it is actually by looking at the plane of the galaxy. So if you're really far away from city lights and you can see the plane of the galaxy, you'll notice these dark spots. And early on in the history of astronomy, we actually thought that these dark spots were holes, places where there just weren't stars. And the early maps of the stars have these sort of places where it looks like there aren't any more stars. But what's really going on is that there's actually obscuring dust clouds. These dust clouds are getting in the way of observing the stars, and indeed to many astronomers, these dust clouds are actually just kind of a nuisance. They wish they'd go away. To me, they're fascinating and beautiful, but many of my colleagues are not so friendly on them. So what's going on here? What's going on with these dusty clouds? How do they work? Well, it turns out that the process is very similar to something you see at sunset. As an astronomer, I'm obliged by the International Astronomical Union to tell you to not stare at the sun. But at sunset, were you to stare at the sun, you would notice that it's much easier to see. And the reason is that a lot of the light coming from the sun is being scattered away by molecules and small particles in the atmosphere. And it's being scattered away more because there's more atmosphere in the way. But there's something else happening. What else is happening is that the sun is becoming red, and all of this is becoming red. And that's because the kind of scattering that we have, that's called Rayleigh scattering, the blue light is scattered away more easily, and the red light makes its way through. It's the same reason that the sky is blue, is that the light from the sun is being scattered around and then scattered back into your eyes. You're seeing blue sky in other directions and red when you're looking through a long path of light. And the same thing happens for astronomers, and that's why we like to use the infrared. So here's a very dark cloud of sooty interstellar medium, and you can see that really you can't see any stars here in the optical. But if you look in the infrared, you can see a lot of stars inside. So this is one reason why Hubble is equipped with infrared cameras, and why James Webb is going to be equipped with even more powerful infrared cameras further into the infrared than Hubble can see, is that we can actually look through all of this dust, peer through this dust, and see lots that's going on inside of these clouds. Now, the way we learn about this dust is through that exact process that I just described, by looking at the reddening of light, right? You can't go out there and get it, except that we can. This is actually data. In fact, this isn't just data. This is an actual interstellar medium particle that was collected by a thing called stardust. Stardust went out there, and it trailed a comet for a while, and it collected cometary material into these aerogels. But then for a while, it actually pointed up towards the the flow coming from the interstellar medium, and tried to catch a couple of interstellar particles. And they turned out to be very hard to track down. You can't actually teach a robot to find these little tracks. This one got named by the person who found it, Orion. It doesn't have much to do with Orion. But we actually have, this was the first interstellar grain that we actually captured on Earth, sort of complete, and were able to analyze. And this was all done through citizen science. So this was done by many, many people, downloading the data and looking through it and saying, oh, I think I found one, oh, I think I found one, and having it verified and having it checked and so forth. And so by that process, we've actually now found 3 of these interstellar grains. So it's very exciting, and I don't know, I think it's a nice pitch for doing citizen science at home. There's a place called the Zooniverse, where you can log on and do all sorts of different citizen science projects, get involved doing science just in your pajamas. Okay, cool. Okay, so that was dirty outer space. Now let's talk about formed from outer space. Let's talk about the process of forming things out of outer space. Some people might call this sort of outer space's most critical role. So back to my favorite diagram. We talked about this with the small stars returning their material back to the interstellar medium, back to the outer space. We talked about this with the large stars through explosions returning their material and disturbing outer space. But now I'm going to talk about this, the formation of small stars and large stars out of outer space. So this is a nearby molecular cloud. This is a region a couple hundred parsecs from here, where some young stars are just starting to be formed. And it's very interesting. The sooty particles that I was just talking about are pretty crucial for the formation of these kinds of regions. So what happens is you have these big clouds of gas, and either through some kind of shock wave or under their own gravity or some kind of combination, we're not entirely sure, these clouds will start to form and collapse into denser and denser regions. But I told you these are molecular clouds, and most of this outer space is actually in an atomic form, just single atoms by themselves. But this gas is actually mostly in molecular hydrogen. So how does that happen? It turns out it's really hard to convince 2 hydrogens to get together and form another molecular hydrogen. When that happens in our atmosphere, it happens due to 3-body interactions. But because the densities are so low, it almost never happens in this kind of situation. So what happens, which is kind of neat, is you have one of those little dust particles I was telling you about, and a hydrogen gloms onto it, and another hydrogen gloms onto it, and over the course of a couple thousand years, those hydrogens wander around, join together, and pop right off. And so that dust, that soot, is actually crucial for the formation of these kinds of clouds. And these clouds are where the stars form. Stars are always forming out of molecular gas. So you need that sooty material. And indeed, early on in the universe, before we had much of this sooty material, it was much harder to form stars. And the stars that formed were very different because they went through a totally different process. So the formation of stars is actually totally governed by this process on dust. So you can walk outside down the hall and see this picture in all its glory. This is the Carina Nebula, and actually just shown earlier today was Eta Carina, the largest star in the galaxy that we know of. And what's amazing about Carina is you're seeing both the formation of stars and their destruction simultaneously. Right? I talked about this process about how if you form massive stars together, some of them will blow up and blow the material away while the other ones are forming. And if we zoom in on this little region over here, you can actually see one of these stars forming. So this is this so-called elephant trunk. This is, as you can see, it's opaque. That's the dust, again, obscuring our view. And in the very tip of this thing, you see this crazy thing going on, okay? And there are these, what are called jets. These jets are shooting out of this little point up here, and they are sending a shock wave through the rest of the material inside the Carina Nebula. Okay? And something that is very strange that we still don't understand is that as stars form, in their process of forming, many of them generate these jets. And as far as I can tell, nobody in the astronomical community actually understands how these things are generated. And what's interesting is they happen on a large range of scales. They happen when you form a black hole, as you're forming a black hole. They happen when you're forming stars. But there's this amazing, beautiful signature of a star being formed. Now, I'm going to sort of zoom in on this. I'm going to choose a closer star because it's a little ways away. And you can actually see this up close and personal. So what you're seeing here, edge on, is one of these disks. And this is kind of a disk where planets form, right? You think about the planets in our solar system, they're all in a disk, and that's because all this gas falls together onto the star, and it's spinning, so it flattens into a plate, and then planets will form in that plate while the star is forming. And what you're seeing here in the red, so you're seeing an edge on, that's the dust obscuring the light from the star. The star is now lighting up this sort of flared out disk. That's why you get that archy appearance here on either side. And then there's this jet that's coming out from the star. So you can see now the star is reacting back on its environment as it's forming. So you're both getting the formation process and the expulsion process simultaneously. And I just have to show this image, which when I was on Facebook like 3 weeks ago, essentially my feed was only this image. It was this image after this image after this image. This is the first image of a high-resolution image from the ALMA telescope in Chile of HL Tau. And at the center here is a star. And what you're seeing here is these gaps. This is not an artist's rendition. These gaps that are being carved out by planets, okay? So as this star is forming, it has a disk, and the planets are actually carving out these gaps. We think that these rings are resonances with some planets somewhere in here that are being carved. It's just unbelievable to see this process of the diffuse universe forming into a star, okay? Pretty much before our eyes. It's really something else. Okay, great. So that was a pretty small scale. We zoomed all the way back into the forming of a star. Now let's go big. So this is our galaxy, if you try to look at it all at the same time. So this is towards the center of the galaxy. This is towards the outside. This is up and down. This is the galactic plane. What I'm showing you here is the hydrogen. This is the hydrogen gas that we're seeing that's floating around inside our galaxy. That's what most of this outer space is made of. A particular focus of my study is these weird little clouds. These clouds are also hydrogen, same scale, and they all have these wacky little names. And what these things are is clouds that are actually falling onto our galaxy. So just like I said that you need to fuel material into a star to form it, same thing is happening here for the formation of our galaxy. So we're really interested in, well, this galaxy keeps forming stars. How is it that it does that? Well, it has to accrete fuel from the outside. And so people are trying to study how this accretion mechanism onto galaxies works. And we can actually see it happening live here at home as these billions of solar masses of gaseous material flow onto the disk of our galaxy to power future star formation. I just love this image of this flocculent face-on galaxy because you can see all sorts of different effects of this outer space all simultaneously. So one effect is this dust, right? And that's what all these dense regions are. But you can also see these beautiful areas where massive stars are forming. Those massive stars are sending out ultraviolet light. The ultraviolet light is ionizing that gas, and that gas is glowing here in a particular transition of hydrogen. So all these little pink objects on the spiral arms are actually regions where stars are forming, lighting up the diffuse material that was forming them. So you're really seeing both the dense regions where the stars form and then the effect the stars have on their dense regions. Really gorgeous. And I don't want to leave elliptical galaxies out of the outer space party. Elliptical galaxies are largely just huge piles of red dead stars. They don't have a lot of gas associated with them, so we typically don't think about them when we're studying this outer space. But another thing that's associated with these guys is massive, supermassive black holes. And those black holes, just like forming stars, shoot out these amazing jets. And so this is a ginormous jet, that's the technical term, coming out of the center of this galaxy. So you're actually seeing the galaxy returning material to the inner circumgalactic medium. So I want to talk just briefly from a somewhat theoretical perspective about how galaxies form. Right? I talked a little bit about how stars form, how material flows into regions where stars form, how stars react back on their environment. So let's talk about that from the same perspective for galaxies. So here's a little diagram. This is the simplest story, the first story we ever told ourselves about how galaxies form, is that, maybe the second story, was that there was dark matter around. The dark matter flowed into a region like this because it was dense in that region. So it basically flowed together under its own gravity. So you end up with these things that people typically call halos. So this is a dark matter halo. And then the gas, not wanting to be left out, around it would flow into that same region. So it sort of felt that sort of depression, and it would flow into that depression. And that's how galaxies would form, is that the gas would flow in and stars would form in the center. So that was sort of our first sketch picture of how things worked. But as we started building sophisticated computers and sophisticated models, which is what I'm showing you right now, we began to realize that there's more to it than that. So here you can see time being measured here, 10 million years at a time. And so this is going to take a while. And what you're seeing here is just a computer simulation of dark matter. So there's no gas here, there's no stars, there's no interesting parts of the universe, there's just the dark matter. But what we learned when we started to run these dark matter simulations was that it's not just that material just sort of flows into these little balls and that's where the galaxies form. It's that there's this crazy network, this what's called cosmic web, as material flows into little balls, these little halos, and then the halos merge together. So this is called hierarchical structure formation. That's the classical term for it. And what you're seeing is the formation of an object that will end up being about the size of the Milky Way. And when we saw these videos for the first time, what we determined was that there must be a lot of merging going on. Merging must be a huge part of the story. It's not just that gas falls into a galaxy and then stars form. It's that their gas must fall into these little halos and then those halos merge. So it's sort of this hierarchical effect. And there's, another 10 billion years of this, so we don't quite have the time, so we'll move on. And that merging is something we can actually see happening right now. So these are the Magellanic Clouds, and like most astronomical objects, they're terribly named. They were not discovered by Magellan, and they are not clouds. The first person north of the equator to discover them, I believe, was a Persian. And they're not clouds, they're nearby galaxies. So this is called the LMC and the SMC, they're nearby galaxies. And they're merging with the Milky Way. So they're basically the closest significant galaxies to the Milky Way. And you can actually see the gas in those galaxies, this outer space, being ripped out of them as they merge. So here's a small galaxy, here's the LMC, here's the SMC, and this is a stream of gas that crosses the whole southern sky. It's basically 180 degrees long. And it's the material that's being ripped out of these clouds as they fall into our galaxy. Okay? So this is that merging happening live. That's something we can actually see with our own eyes. It's really pretty astounding stuff. This is you can't see it with your own eyes. It's a radio telescope image. Okay. This is a more extreme example. This is a galaxy about the size of the Milky Way, but it's inside a cluster of galaxies. And that cluster is full of this outer space. Now, the outer space is very, very low density in a cluster of galaxies, but this galaxy is falling into it fast enough that it's feeling a headwind, okay? Can you see that it sort of looks like it's being ripped apart by a wind that's blowing past it? So as galaxies fall into these clusters, they actually get shredded apart, and you can see this dust here, the dusty interstellar medium, is being torn out of this galaxy. So this process of galaxy formation, of merging, and of the collision of galaxies really is very easy to study when you actually end up looking at the gas. And this is a classic example. This is the antennae galaxies. And you see these beautiful tails, these tidal tails that were mentioned earlier. And when you see the galaxies colliding, you can actually see what's going on here is a huge amount of formation of stars. So what we know is that when galaxies collide, their interstellar media collide. That creates huge shock waves, and the shock waves generate a huge amount of star formation. You get these really dense areas where stars want to form. So you tend to find that when you are looking at galaxies that are interacting, there's an extra star formation going on. So the diffuse material, this outer space, is crucial for the formation of stars, especially in the context of the collision of galaxies. So that's the second story we told about the formation of galaxies. The third story we've told ourselves, and I think this is maybe the most compelling right now, is this idea that material flows into galaxies in these rivers. Okay, so this is a simulation. This isn't an observation. That's a disk of a galaxy. This is done by my colleague Ryan Jung. And this is, you can see, at a very large scale, so almost on the megaparsec scale. But you see these beautiful long tendrils of material that flow into the galaxy. And it turns out all those little halos that we saw, all those little tiny things that merge together, not all of them actually have stars in them. And it turns out that all that merging we're seeing might be a bit of a red herring. Really what's going on, we think, is that material is flowing in on these huge streams, and as it flows in, some of it will heat up, and some of it will cool down as it flows in and will merge onto the galaxy. And it's actually that process that's dominating, that's most important for the formation of galaxies, the flow of material onto the surfaces of the galaxies from beyond in these beautiful, huge rivers. And so we're all building telescopes now to try to track these rivers down and see what we can see. The other thing that's really important, and I think this is sort of the cutting edge now in terms of understanding how galaxies work, is to understand this process of feedback. Okay? So what you're seeing here is hot gas from the Chandra observations, the dust in red from the Spitzer Space Telescope, and then the disk of the galaxy here. This is, I forget which galaxy this is off the top of my head, and the disk of the galaxy here from Hubble. And what you're seeing is this process called feedback. Okay? When we ran our original computer simulations to try to figure out how galaxies worked, we always made too many stars. Every galaxy we made, it seemed like, why are there so many stars in these galaxies? That's not how the universe looks. And the key ingredient that we were missing is the fact that when stars die, they affect the gas that's in the galaxy. They blow back, right? You saw all those beautiful images of these stars disturbing, those bubbles flowing out, the carving out of the molecular clouds. That's crucial, it turns out. That's actually critical for how galaxies form. If that didn't happen, the universe wouldn't look the way it does. And you're seeing this on a really grand scale in the starburst galaxy, where you have lots of stars forming in the center. They're emitting a huge amount of energy, and they're blowing the galaxy apart. And so that has a mitigating effect on the speed at which a galaxy can form. So that turns out to be a really crucial part of galaxy formation. Now we're going to go out to the biggest scales. This is a galaxy cluster. This is the nearest cluster of galaxies, called the Virgo cluster. In orange is the X-rays. What you're seeing here is all the gas, the neutral gas for each one of these galaxies. These galaxies are blown up by a factor of 10, so you can see them with your eyes, otherwise they'd be too small. And what you're seeing is that on the outskirts of the galaxy, outskirts of the cluster, there's a larger number of these galaxies that have lots of gas, but as you get towards the center, they're being shredded apart. They're feeling that headwind I was talking about. All their gas is being removed and is being added to all of this gas that's in the cluster itself. So you see this relationship between the galaxies and their gas, and then the gas, this outer space that's floating through the cluster. And I'll just leave you with this. This is a simulation of the formation of many clusters of galaxies. Each one of these points is a galaxy. All these flows of gas into this cluster as it forms. I think this is just a beautiful demonstration of this sort of cosmic ballet that's ongoing, that's telling us something about how our galaxies form, how our stars form, how our planets form, and how we form, and how this is so deeply related to the outer space that we're all living in. And I'll leave it there. Thank you.